Now today we are going to start a new chapter, that is thermodynamics. Alright, a new chapter is thermodynamics. Now the question comes, what do you understand by thermodynamics? What is exactly thermodynamics? Before starting the chapter you should know that what we are going to study in it. What is there in this particular chapter that we are going to study. Now, it's a branch of science which deals with the study of different forms of energy. Different forms of energy. You'll be studying internal energy, what you can say enthalpy. Then you'll be studying about thermal energy. You'll be studying about what you can say entropy. So many different you'll be studying about. So, it is a branch of science which deals with the study of different forms of energy and the quantitative, what you can say, meaning or the quantitative relationship between them is known as thermodynamics. The different forms of energy which I said you, like internal energy, enthalpy, entropy, free energy, thermal energy, so many different kinds of energy you will be studying. Not only we will be studying about the energy, but what is the relationship between them? What is the relationship between internal energy and enthalpy and entropy, or entropy and free energy, and so many. Alright, so that we are going to study about it. So basically we came to know in this particular chapter we are going to study about the energy and the relationships between this particular energy we are going to study here. Alright, in this particular chapter, that is thermodynamics. Okay, now here are certain terms. To start the chapter we need to study certain terms. The first is your system and surroundings. System and surroundings. The first is. So what is a system and what is a surrounding? The part of the universe that is chosen for thermodynamic considerations. That is the part of the universe chosen for thermodynamic study. Alright, there is a study of temperature, pressure, concentration, volume, etc. We can say that is called a system. The part of the universe that is chosen for thermodynamic study. Alright, which consists of temperature, pressure, volume, concentration, internal energy, and so many other things we can say that. That is called as a system. That is known as a system, we can say that. The part of the universe. And the remaining portion of the universe which excludes all these things. Alright, remaining portion of the universe which excludes what I talked to you, the temperature, pressure, volume, and all these things. We can say that. It's known as what? Surroundings. Now, let me, what you can say, explain you in simple words. Now, this is a definition I said you. The remaining part of the universe which is not in our study, which is not concerned in the thermodynamic study. Alright, which is not, what you can say, we are going to study in it, but we are not going to deal with it. Not directly, indirectly we can say that. We are going to deal with it. So, that is called as the surroundings, we can say that. So, here universe means system plus surroundings. What is it? Here universe does not mean, I mean to say the sun, moon, earth, Jupiter, planets and all these things. No, here the universe means basically, in simple language, it is known as your chemistry lab. We can say that. Here the universe means. So in the chemistry lab, when you are doing the experiment, alright, for example, let us say you have taken some mercuric oxide and you are heating it. You have taken some mercuric oxide and you are heating in a test tube. Alright, so mercuric oxide is your system. And regarding mercuric oxide, the observations which you are going to see, that is coming under system. That is a change in color, there is some evolution of gases, there is a change in temperature, and so many other things which is going to happen. The observations basically, that is known as a system. And the test tube, the Bunsen burner, the test tube holder, the glass rod, or whatever it is you are taking it to carry out this particular system is known as the surroundings. Now we are not concerned with the test tube holder, the Bunsen burner, the glass rod. Are we concerned of? No. But without that also can we carry out the system? No. That also is not possible. So system is that part of the universe which is concerned in our study. And surroundings is that part of the universe which is not in our study. But without surroundings, system is not possible. As I said, if you are heating mercuric oxide without Bunsen burner, without test tube holder, without the glass rod, and without the apparatus, is it possible to carry out? No. So that is called a system. I hope you understood what is a system and what is the surroundings. Now, next is what you find is that is we are having three different kinds of system. Under system, we are having three different kinds of system. What is that? That is, system is of three different types, we can say. One is your open system, another is your closed system, and the third is your isolated system. Open, closed, and isolated system. Now, what is an open system? A system is said to be an open system if it can exchange both matter and energy with that of the surroundings. If it can exchange both matter as well as energy with that of the surroundings, that is called as an open system. As I said, you have taken some mercury oxide in a test tube and you are heating it. Alright. So what happens is that not only on heating mercury oxide, what happens? HGO upon heating will give you Hg plus O2. Oxygen gas is being released. Not only the oxygen gas is released, along with some energy is also released. Alright, for example, suppose you have taken a test tube, you have taken some zinc granules, you have taken it, alright, and you have added HCl into it. On adding HCl to the zinc granules, what happens? Zinc reacts with HCl or zinc reacts with H2SO4. You can take H2SO4 also, understood? To form salt and hydrogen gas is released. Let us say you have taken HCl. It is going to form zinc chloride and hydrogen. If you take H2SO4, it will form zinc sulfate and hydrogen gas will be released. So if the test tube is open, this gas will be released into the atmosphere, as well as some heat also may be released or heat may be absorbed. So when what you can say matter, here matter means the product and the energy, the gases or the energy which is released, we can say that. Clear? So when both are exchanged in the system and the surroundings, that is called as nothing but known as an open system. Or simply you can say you have taken a vessel and you have taken some water and you are heating it. An open vessel, like in your house, your mother has taken a particular tumbler and she has put some water in the tumbler and she is heating in the gas oven. So what happens? After some time the water vapor comes out and energy is released, we can say that. So what is that? That is known as an open system. Now what is a closed system? Closed system is, if a system is said to be a closed system if it can exchange only energy but not matter with the surroundings. Alright, it is called as a closed system. If it can exchange only energy but not matter with the surroundings. All these examples which I said you just now to you. For example, I said you take a tumbler and you put some water in the tumbler and you heat it. Now what I do is that I put a lid upon the tumbler. Let us say. Alright, tumbler means understood. Dekchi, let us say. Hindi mein jisko dekchi bolte hain. Alright, I am putting a lid upon the tumbler. What will happen? Water vapor cannot come out. Only the energy can be radiated out from the walls of that particular tumbler, we can say that. Only energy can be radiated out. Suppose for example, you have taken a test tube, you are heating mercury oxide. You have put a cork at the mouth of the test tube. What happens? Oxygen gas cannot be released because you have put a cork at the mouth of the test tube. Then what will happen? Energy will be exchanged. The energy will be radiated from the walls of the test tube. So in this way, this is considered to be as a closed system. In a closed system, only energy is exchanged between the system and the surroundings, but not matter. When energy is exchanged but not matter, it is said to be as a closed system, so to say. Now next is isolated system. The third is your isolated system. First two we have finished, open system, closed system. The third is your isolated system. Now isolated system means as if a system can neither exchange matter nor energy with the surroundings. That is called as an isolated system. What I said? If a system can neither exchange matter nor energy with the surroundings, it is called an isolated system. Means, for example, you have taken some hot water and you put it in a that is it is said that is known as flask. You have put it inside a flask. So and you have closed the mouth of the flask. Alright, what do you find? Is water vapor exchanged into the surroundings? No. Is heat exchanged between the system and the surroundings? No. It's a thermos flask. It keeps the hot things hot, we can say that. You know that for some time. So in this way, what you find that it neither matter nor exchange is exchanged between the system and the surroundings. For example, you have taken a teapot. Teapot you have taken, you have put some hot tea into the pot and you have closed the mouth of the teapot. What do you find? Neither matter nor exchange and nor energy is exchanged between the system and the surroundings. It forms an what? Isolated system. It forms an isolated system. So in this way, where neither matter nor energy is exchanged in the system and the surroundings, it is called as an isolated system. When only energy is exchanged but not matter, it's a closed system. But where matter as well as energy both are exchanged in the system and the surroundings, it is known as an open system. Alright. Now can you tell me an answer? We human beings, are we coming under open system, closed system or isolated system? We are coming under open system. Do we come under open system, closed system or isolated system? We come under open system, where matter, we are releasing the gases as well as energy in the system and the surroundings, isn't it? So we can come under open system, mind it, the human beings. Now, after that, this system is being governed by some state. Alright, some state of the system is there. There is some certain state of the system. There is certain variables are there, which are called the state variables are there. Alright. Now, the state of a system means the condition of a system which is nothing but describes in terms of observable properties like pressure, volume, temperature, etc. is known as the state of the system. Alright, what I said? The state of a system means the condition of the system which is described or which describes in terms of what you can say temperature, pressure, volume, etc. That is called as the state of the system. We can say that. Got it? So based upon that, we have got a state function and we have got a path function based upon that. Now state function means a physical quantity is said to be a state function if its value depends only upon the state of the system. Got it? Again I repeat, a physical quantity is said to be a state function if its value depends only upon the state of the system and does not depend upon the path by which the state has been attained. It does not depend upon the path by which the state has been attained. Alright, that means it depends, in simple words I should say, which depends upon the initial and the final state only. Alright, it depends upon the initial and the final state. It does not depend that how that initial and final state has been attained. That is called as a state function. Again I repeat, that is a physical quantity is said to be a state function if its value, listen carefully, if its value depends only upon the state of the system and it does not depend upon the path by which the system has attained this particular state. Alright, means what you find is that, for example, temperature is a state function. We can say that. We say initial temperature, final temperature. Energy is a state function. Alright. Then final energy, initial energy. We say volume is a state function. Alright. Now, for example, let us take temperature. Let us say temperature is I am taking it. Now, what I said, temperature is a state function. Depends upon the initial and the final state. Now, for example, this body is there. Let us say. Now, I record a particular temperature. Let us say 40 degrees Celsius. Now, whether initially let us say the temperature was 20 degrees Celsius. Now it has reached to 40 degrees Celsius. Got it? Initially it was 20. At room temperature, let us say, now it has come to 40 degrees Celsius. Now I am not concerned of that whether this body has attained this particular temperature by losing or by gaining. By losing heat or by gaining heat. I am not concerned of. Got it? To record the temperature of the system, am I seeing that how this body has attained this temperature by loss of heat or by the gain of heat? Only we are seeing what is the initial temperature and what is the final temperature. Suppose I have to measure the change of temperature. Then what I have to see? Change of temperature is what? Final minus initial. That much only. So when I calculate final minus initial, am I seeing what is the path by which it has attained this final temperature and what is the path by which I had attained the initial temperature? Not at all. We are not concerned of. Means the temperature 40 degrees Celsius it has attained, whether by losing or whether by gaining, I am not concerned of. You can say that yes, 20 degree means by gaining only it has what you can say 40 degree. But when I said 20 degree, then only we came to know what in a. Initially I said 20 degree, then only you came to know, oh 20 degree, initially 40 degree means it has gained. But when you do not know the initial and the final temperature, alright, and you have to calculate the change in temperature. Suppose I am asking you children, you calculate the change in temperature of this particular body. Then what you will do? You will ask me, sir, what is the final temperature? What is the initial temperature? Isn't it? Will you say me, sir, that what is the path by which has attained this? Not at all. For example, a pond is there. If you have not understood the example, I am giving another example. A pond is there. You are filling up the pond. Alright. Now, the pond is being filled up. Alright, with water. Whether by rainwater, or whether by pumping water from another pond or from another source, that is from well or a river, or we are not concerned of. If I have to consider the change in volume in that particular pond, what I need to see? I need to see the initial volume, I have to see the final volume. This is a change in volume. Finished. Isn't it? Suppose initially some water was there in the pond. Now I am filling up the water. Now, how I am filling up the water? It is not concerned. I am not concerned of. When I calculate the change in volume, try to understand. When I am calculating the change in volume, am I concerned of that the water has been filled in the pond? There is a change in volume. There is an increase in volume by what you can say rainwater, or by some tubal water, or by some water pumped from some other source. Am I concerned of? No. When I am considering the change in volume, I am not concerned of how the volume it has attained, the final volume it has attained. Alright? I am not concerned of. So when what you can say, a system, when a state of a particular system, when a variable does not, when a physical quantity does not depend upon the path by which it has attained that particular state, then that is called as a state function. Alright? It is known as a state function. For example, suppose a person is going from the first floor to the fourth floor, let us say. A person is going. Now, I am not concerned that when a person is going from the first floor to the fourth floor, that when I am considering the energy, let us say. Alright, when I am considering the energy, I am not concerned that how that person has reached that particular energy. When a person is going from the first floor to the fourth floor, listen carefully. A person, whether he is going by the help of the lift or whether he is going by the staircases to calculate the change in energy, I am not concerned of. I will say what is the initial energy. Here initial energy means potential energy, definitely. Alright, because he is in the first floor or in the ground floor and he reaches to the fourth floor. So there is a change in height. So I am considering the potential energy. So for considering the potential energy, I did not have to see whether that person has reached the fourth floor by the help of the staircase he has gone, or whether by the help of lift he has gone. To calculate the change in energy, I am not concerned of. But to calculate the work, alright, I don't say change in work. You have never heard the word change in work. You have never heard the word change in heat. Got it? You have never heard the word change in heat. You have heard the word change in temperature, change in volume, change in pressure, change in temperature. Because all these are state function. You have never heard the word change in work. Got it? Because work and heat, listen carefully and note it down also. Work and heat, both are path function. Both are path function. Now, how can I say that work is a path function? What I said, to calculate the change in energy, I am not concerned of whether the person is going with the help of the lift or whether the person is going with the help of staircase. I am not concerned of. Definitely not. But to calculate the work, got it? The man is going with the help of the legs, definitely. So his legs is doing some work. Now don't say, sir, in physics, that is both it is same, whether he is going with the help of the lift or by the staircase it is same. No, I am not talking here about the mechanical work also. Let me also make it clear to you. That also let me make it clear to you. That is known as a mechanical work. I am not talking to you about that. Got it? So it is the, what is that? Nothing but it is known as a physical work. Or if some gas is being taken inside it, then it is known as a chemical work. Alright, try to understand that. Don't get mix up. Don't mix up all those things. Now, what I said is that if a man is going with the help of staircase, definitely he will take the help of the legs. His legs is doing some work. His legs is doing some work. Got it? But if a man is going with the help of the lift, then his legs is not doing any work. Got it? So when I am saying a man is going with the help of the lift, when I am saying a man is going with the help of the staircase, his legs is doing some work. That means I am giving you a path. That is known as a path function. I am describing a path. I am defining a path. So hence it is a path function. Alright? To define the work done by the person, the work done by the man, I am defining a path, that whether he is going by the help of the staircase or whether he is going by the help of the lift. I am defining a path to you. So there I don't say what is initial work and what is the final work. As initially only I said you have never heard of also that what is initial work and the final work. You have heard of initial energy and final energy. Got it? Even if work and energy both they contain the same unit, that is the joules. Got it? But still then work is a path function and energy is a state function. Got it? Got the difference now? Similarly, heat. When I am heating this particular body, got it? So I am describing a path. How I describe a path? You read in lower classes that I am holding this end and I am heating this particular end. So what we say, the heat energy travels from one end to the other end. How it travels? That is the heat energy gained by the molecules. It transfers this energy to the neighboring molecules. It collides with the neighboring molecules. It transfers energy to the neighboring molecules. And thus that particular molecule transfers energy to the next neighboring molecules. Which is otherwise I can say in simple words, I am talking to you about the kinetic molecular theory of matter, which you have studied in the lower classes or in previous chapters. So according to the kinetic molecular theory of matter, when I am heating a particular substance at one end, let us say a metal rod, I am holding a metal rod, let us say, I am heating at one end, this end. After some time, I will not be able to hold this particular end. I have to drop this metal rod. I have to drop it. Why? Because the heat energy travels from one end to the other end. That is from the hotter end to the cooler end. How it travels, I have explained you. Got it? So when I am explaining what I am giving you, I am giving you a path. So hence it is called as a path function. So heat is a path function. Work is a path function. Except heat and work, all are state functions. I hope you understood this. Now next is we will come to the properties. We have studied about the system. We have studied about the state of the system. Now we are going to study about the properties. So properties is basically divided into extensive properties and intensive properties. What I said? Extensive and intensive properties. Extensive properties and that is intensive properties. The first I will study extensive properties. Now these are those properties which depends upon the quantity of the matter contained in the system. It depends upon the quantity of the matter contained in the system. Quantity of matter means mass. We can say that. Quantity of matter is what? The mass. Alright. But it does not depend upon this, what you can say, the nature. It depends upon the quantity of matter present in the system. That is called as the extensive properties. The examples are mass, volume, heat capacity, then we can say internal energy, enthalpy. This depends upon the quantity of matter. So these are coming under extensive properties. Now intensive properties are those properties, next we will come to the intensive properties, the second one. Intensive properties are those properties which depend only upon the nature of the substance. Listen carefully, which depends only upon the nature of the substance. I am talking of the second one, intensive. Which depends only upon the nature of the substance and is independent of the amount of the mass present in the system. We can say that. Clear? So it does not depend upon the mass, which is independent of the mass, which is independent of the amount of the substance present in the system, but it depends upon the nature of the substance, which is known as an intensive properties. Again I repeat, these are those properties which depends upon the nature of the substance and is independent of the amount of the substance present in the system. It is called as an intensive properties. The examples are temperature, pressure, refractive index, viscosity, density, mole fraction, etc. These are coming under intensive properties, which depends upon the nature but does not depend upon the mass. Now here I give you an example, that is your temperature. Temperature is an intensive properties, I said, which depends upon the nature, it does not depend upon the mass. How can I say that? Very simple it is. For example, in your house, inside your house, you have stored water in different places. Let us say you have kept water in a glass. Let us say you have kept water in a bottle. Let us say you have kept water in a tumbler or in a big container. You have kept water. Will you find the temperature be different in different this container? For example, in a glass you have kept some water. Will it be different temperature? Will it be different temperature when you have kept the water in a bottle? Will it be different temperature when you have stored the water in a steel tank? Will the temperature be differing? No. Got it? No, it will not differ. We can say that. Why? Because temperature is an intensive properties. It depends upon the nature. It does not depend upon the mass of the system. Got it? Does not depend upon the mass. So hence temperature is an intensive properties. We can say that. Clear? Similarly, pressure, it's an intensive property. Got it? Now, how can we say that pressure is an intensive property? Because pressure is what? Pressure is nothing but force exerted per unit area. Now remember that extensive by extensive is intensive. Alright? Extensive by extensive is intensive. What I said you, pressure is equal to force per unit area. Pressure is equal to force per unit area. Now these two are extensive. So hence pressure is an intensive properties. We can say extensive by extensive is intensive. Similarly, mole fraction. It is an intensive properties. Mole fraction is what? It is depending upon nothing but the moles of the component by total number of moles. Isn't it? For example, mole fraction of water. Got it? For example, you have taken a sugar solution and you want to calculate the mole fraction of water. Already you have done it. How to calculate, you know that. So what you will do is that number of moles of water by total number of moles. Total number of moles means number of moles of water plus number of moles of sugar. So both are extensive. Alright, number of moles of water is an extensive property. Total number of moles of water plus sugar, that is also an extensive property. So two extensive is intensive. In this way, extensive properties are those properties which depends upon the mass, which depends upon the matter, amount of matter present in the system, but does not depend upon the nature. But that is an extensive properties. And intensive properties are properties which depends upon the nature but does not depend upon the mass. I gave you so many examples and I explained you also. In this way, what you can find is that extensive will give you an intensive property, we can say that. Now, next, after this, we'll come to that is process. Alright, we studied about the system, surrounding, system is open, closed, isolated. Then we studied about the state of the system. That is, it can be state function, it can be path function. Then we studied about the properties. Now we are going to study about the process. Alright, so process, that is known as a thermodynamic process. Here the process, when I say, it is related to thermodynamics, isn't it? The thermodynamic process. Now the thermodynamic process is of three kinds basically. What is that? The first is your isothermal process. Now from the word itself we can guess. From the word itself. Isothermal process. Isothermal. Iso means equal. Thermal means heat. So when a process is carried out in such a manner that the temperature remains constant throughout the process, it is called as an isothermal process. Alright, again I repeat. When a process is carried out in such a manner, such that the temperature remains constant throughout the process, it is called as an isothermal process. That means delta T is equal to 0. Small t, capital T is time, we can say that. So in this way, neither in such a case, in such process, what you find is that heat can flow from the system. Alright, that is when such a process is carried out, that is heat can flow from the system to the surroundings and vice versa in order to keep the temperature of the system constant. We can say that heat can flow from the system to the surroundings and also vice versa. Vice versa means from the surrounding to the system also it can flow, due to which the temperature remains constant. That is called as an isothermal process. Next is your adiabatic process. Adiabatic process. Now here the word of course does not say, but you can know the meaning of the word adiabatic. So when a process is carried out in such a manner that no heat can flow from the system to the surroundings. Got it? That is, the system is completely isolated from the surrounding. It is called as an adiabatic process. No heat can flow from the system to the surroundings. That means heat remains constant, we can say that. It is known as an adiabatic process. Heat is noted with the letter small letter q. Heat is noted with the small letter q. So here delta q is equal to 0 in case of adiabatic process. Alright, I said it. Next, the third one I said is isochoric process. Isochoric process. Isochoric means when the volume remains constant. Delta V is equal to 0. Got it? It's a process in which the volume of the system is kept constant. Volume remains constant. It is known as isochoric process. One more also we can add it to it. Known as isobaric. You know that this particular one, this word isobaric. process. Isobaric means bar is a unit of pressure. So when the delta P is constant, when the change in volume is constant, when the pressure remains constant, alright, it's the process in which the pressure remains constant, that is said to be as an isobaric process. Now if you draw a graph of P against V, look here, if you draw a graph of pressure against volume, then this is your isochoric, where the volume remains constant. You can see here. See, it's a straight line I am drawing. This is isochoric. This line is isochoric. Now, when the pressure remains constant, this is isobaric. Let me write it there. Isobaric. And here, how will I write? That is isochoric. Isochoric. You can see that. Now, next is we can have isothermal and adiabatic. This is isothermal and this one is adiabatic. This is the graph we got it. Okay, the pressure volume graph I should say. This is your isochoric. If you don't understand, let me write the I in this way. So this is your isochoric, volume constant, this is isobaric, pressure constant, this is isothermal and adiabatic. Isothermal temperature constant, adiabatic means heat constant. Thank you.